All right, so we're going to use inverse functions. Pretty new stuff, so hold on, let's go. Inverse relation interchanges the input and output values. Not sure why I just did that. Output values, which means you switch the x and y's, the original relation. Whenever you see the word relation, it means a set of ordered pairs, any set of ordered pairs. So all we're going to do to get the inverse is you switch the x's and y, which means the domain and range are also interchanged. So I'll put an example down here. If I have this relation, a set of ordered pairs, 4, 5, 6, 7, 8, 9, 1, 2. The inverse is just switching your x and y's, or interchanging them, 5, 4, 7, 6, 9, 8, 2, 1. Really hard stuff right there. So inverses, get that in your mind. When you do an inverse of a function, you just interchange the x and y, or the input-output, or the domain and range. All right, the graph of an inverse, this is a pretty cool thing here. When you have two relations and you're going to graph them, they're always going to be reflections over the line y equals x. And the line y equals x is that green one in here in your graph that goes through, it's this one right here, the green one, that goes through 0, 0, 1, 1, 2, 2, 3, 3, because it's where y and x are equal. And I graphed the blue line there, which is y equals 2x. And then I found the inverse of that equation. When I found the inverse, it's the red line. And look what happens. Look what the green line does. It splits them right in half. The blue line and the red line are reflected across that line. And that is always true with inverses. So that's one way you can tell if two equations are inverses of each other. You can graph them both and then see, and also graph the line y equals x and see if they're reflected across that line, see if they're reflections of each other across that line. This says find the inverse. To find the inverse of a relation given by an equation, there's really two steps to it. Number one, you take the x and y's and you switch them, and then you solve for y. And I'm going to show you one right here. The bottom part here says find an equation of the inverse for this relation, y equals 3x. So what I'm going to do first here is I'm going to switch my x and y, which is kind of a weird step when you think about it. Then your job is to solve for y. So I'm going to take the 5 to the other side, make it x plus 5 equals 3y. Then I'm going to divide both sides by 3. So I get y equals x plus 5 over 3. And that's the inverse of that one. Now, you could also write it, if you could divide each term by 3, you could get 1/3 x plus 5/3. That's exactly the same thing. So either that or this, either one is fine. All right, the next thing we have today is it says functions f and g are inverses of each other, provided that. So they're going to give you two functions and ask you if they're inverses or not. And here's how you can tell. This is composition like we did, the other day. So it says f of g of x equals x and g of f of x is x. If both of those are true, if you do both compositions and you get x both times, that means the two functions are inverses of each other. And you're going to see a symbol like this, like f negative 1 power. If you see that, that means f inverse or inverse of f. You can write it either way. F negative, f inverse or inverse of f. So whichever way you want to go there. So in blue down here, I put verify that those two functions are inverses of each other. So what I'm going to do first, I'm going to do f of g of x. I'm going to do the first composition. And when you do f of g of x, you're taking function g and plugging it into the f where the x is. So just like we did the other day. So I'm doing 3 times 1/3 x plus 5/3. And don't forget the little minus 5 out there. I just put it in where the x was. Distribute the 3, you get x plus 5 minus 5. When you work that out, you just get x. And now let's go g of f of x. Got to do the other way also. You must do both. So this time I'm going to plug function f into function g, where the x is. So it's going to be 1/3 times 3x minus 5. And don't forget the plus 5/3. So if I distribute the 1/3 there, I get x minus 5/3 plus 5/3. And look at those 5/3 are going to cancel. You just get x both times, and you're good to go. Okay, so all we've looked at so far today are just linear functions where we had no exponents involved or anything. Inverses of power or nonlinear functions work the same way, but you got to be careful on one of them. And as you can see here, I have one that says f of x equals x squared. That's the first one, which is being an even function. Second one, I have g of x equals x cubed, which is odd. And the first one, the f of x equals x squared, is a parabola. But if you look at the inverse, I went ahead and just graphed the blue is the original function, the red is the inverse. Obviously, the red one does not pass the vertical line test, which means it is not a function. All right, that's not a function because it fails that one. Whereas the odd one over here, they're both functions, so we're good to go. So what we have to do when we do an even one is we have to do something called restricting the domain. We have to restrict the domain to only non-negative numbers. So what we're going to do when we graph these or look at them is we're going to restrict it. We're going to say, okay, we're going to take that part of the graph, that part right there, and also of the inverse, we're going to use or take this section right here. Because if we take those two, it's kind of hard to see there because I made it way too thick. But if you can just take those two, both of those would be functions, and they also, well, I can't tell you that yet because you don't know, but that's what we're going to do. If it's even, we're going to have to restrict the domain to just positive or non-negative numbers, whereas with the cubic or the odd functions, we're pretty much good to go like we did the linear the same way. I know this isn't making a whole lot of sense yet. Let me show you a quick example. All right, this one says, find the inverse of f of x equals x squared, as long as this is true. X is non-negative, x is 0 or greater, then graph both of them. So the inverse would look like this. Remember, first I'm going to put the y in. Once you put the y in, you switch the x and the y, like we always did. To get the y by itself, I got to take the square root of both sides. So technically I would do this, but because we're limiting or restricting our domain, I'm only going to use this, just the positive square root of x. That way it will pass the vertical line test and it will be a function. So if I graph them, the original function says y equals x squared. That's a parabola, but I'm just using, look at this, just the positive part of the parabola. So when I start the parabola right here, it would go up 1 over 1, and it would, the parabola's doing this. Now when I graph the inverse, the square root actually does this. That starts the same place. It does this. That was like half of a sideways parabola. And if I did draw the line y equals x, which you don't technically have to do, it would go right through here. It would split it. It would be reflections. They would be reflected over that line. I'm having a hard time making it show up. Okay, it'd be reflection over that line. So if it's an even degree, we're probably going to restrict the domain. We are going to restrict the domain. If it's an odd degree, we're good to go. All right, last thing here, horizontal line test. The way you can tell if an inverse function is also a function or not is if it passes the horizontal line test, if a horizontal line touches the graph only once. The graph you're looking at here in the very first one, that's an odd one, that's actually x cubed. And then no matter where you draw a horizontal line, I can only touch the graph one time, which means it's called one-to-one, which also means it is the inverse is a function. Now, this is an x squared graph or an even degree graph. If you look at that, a horizontal line hits it more than once, which means the inverse is not a function, and that's why we have to restrict the domain if we're going to try to find it. Okay, so that's how you can tell horizontal line test, and we can check those on the calculator as well. Okay, last slide. Graph the function y equals 2x cubed plus 1, determine whether the inverse is a function. So if I graph y equals 2x cubed plus 1, just to save some time here, you can punch this in your calculator to kind of check me out here, but the graph, it's been shifted up. Once an x cubed graph, it's going to do this kind of thing. It's going to look kind of like this. It does pass the horizontal line test, which means the inverse is a function for sure. And then it says, okay, if that's the case, then find the inverse. So I'm going to find the inverse. So I'm going to switch the x and y's, just like this. Now I got to solve for y. So I'm moving the 1 over. I'm dividing by 2. Which would be x minus 1 divided by 2 equals y cubed. And because it equals y cubed, I got to take the cube root, and the cube root of all that would be x minus 1 over 2. The cube root of x minus 1 over 2. That's terrible. Let me try writing that again. Sorry about that. X minus 1 over 2. There you go. So hopefully not too bad today. The work's really not that hard at all. A few words and terms you need to make sure you know. Hope you got some good notes on this. Be good to go back and look at them. And I guess that's it. I'll see you tomorrow.